Hello everyone, welcome back to our channel. Today we are diving into one of the coolest concepts in chemistry, that is the Lennard-Jones curve. This graph explains why the atom stick together to form molecule like H2. If you have ever wondered how bond forms or break or stick around, this 4-minute explainer will make it crystal clear. So let's jump in. First, let's break down this curve. Okay, on the x-axis we have internuclear distance. That's just the space between the two hydrogen atoms. That is the internuclear distance, basically the distance between the nuclei of the hydrogen atom. Okay, it is measured in angstrom, where 1 angstrom is 0.1 nanometer. On the y scale we have free energy. Okay, high energy, that is on the top, means unstable. Low energy, that is bottom, means stable. The zero line is our reference. That's the free energy when atoms are far apart and not interacting. So you can see this situation where they are far apart and not interacting. Now look at the curve itself. It's like a roller coaster. You see that? Starting from the left, when the two hydrogen nuclei are really close, less than 0.74 angstrom, this distance basically, the energy shoots up. It's very high, it's positive because the nuclei are very closer and there is a nuclear repulsion taking place. So nuclei repel each other like the magnets pushing apart. There is no bond here, just chaos. So very high energy. As we move right, the distance increases. You see, the distance increases and energy drops dramatically. And the energy drops and it hits minimum at exactly 0.74 angstrom right here. That is the sweet spot, the equilibrium bond distance for hydrogen. Here the atoms are perfectly balanced and the positive nuclei are attracted by the sharing electron in overlapping orbitals. It's like a cosmic hug. So here these two atoms will be feeling most comfortable, where the bonding will be taking place, and this length actually will be the bond length, and this energy will be basically the bond energy. See the little diagram on the graph basically. They show the process, separate hydrogen atom with their electrons and then coming together, right, to form finally HH bond here. And then they are pulling apart again. When they are forced to come even closer, then the nucleus repulsion dominates and again energy rises. The minimum energy point is the key here. It's where the molecule is most stable. This is the place where they are very happy. And to form the bond from the separate atoms, energy is released, making it favorable. Okay. But what if you stretch for the post 0.74 angstrom? If you move further, the energy start rising again. Okay, like here, this direction. If you move again, energy start rising, right, and it comes to 0. So the orbitals basically stop overlapping. Here is the overlapping, and now if you move further, they stops overlapping and there is no bonding. The atoms just drift apart. Now the red arrow on the graph basically, you can see it. It is actually the value of bond energy at around 104 kilocalorie per mole for hydrogen. It's the energy basically that you need to input to break the bond and separate the hydrogen atom back to infinity. Okay. So in real life, this curve is not just for hydrogen atom. It's a model for all the interacting, gas or solids molecules. It's named after Lennard-Jones, who figured out this balance between attraction and repulsion. So to sum it up, if too close the atoms are coming, too close means this is the part, then repulsion increases basically, into nuclear repulsion basically increases and there is no bond formation. Okay, and if they are far away also, there is no much interactions, no bond formations. Okay, so bond forms, energy should be minimum. So here is the bond formation taking place where the energy is what, minimum, and that's why molecule exists. So that's all about this Lennard-Jones curve. Thanks. If you like my video, please do like and subscribe my channel. Thank you.